Okay, good afternoon, everyone. Um, so it is time to start. So today we'll be looking at our frequency domain dynamics, the actual final logical development towards developing a control system. So in the session, we'll be reviewing the logic of developing our approach to finding our control system. And then we'll be doing an example that takes us all the way to tuning a PI controller. 1 second, please. Okay. So let me just share screen here. Okay, tell me, can you all see that? I think someone getting some feedback from one of the okay. So here's the basic theorem, and we showed the proof of this basic theorem last time. And we want to look at now using this basic theorem to enable our development of our control strategy system. So just first talking about what this basic theorem is telling us. It's saying that if we have the magnitude ratio as a function of omega, then we get the magnitude of g of I omega. So what that means is if we have a process, so let's just sketch it here. So this is something I explained last time, but if we have some process, and let's say it's a black box to us, we don't know what's going on in this process, and we have some input to this process. So there's an input here and an output here. And if we apply a sine wave at this inlet, right? So let's say this, this control variable is an inlet flow rate. So if we apply a sine wave at the inlet point, right, as you did in the practical, right, you saw you can apply a sine wave at the input. And then if we collect the output, so let's say the output looks like this, then we know that we can collect two pieces of information. One is we can collect the amplitude here. And then, of course, we also have a different amplitude, which is here. So on the input side, you can also define an amplitude. So you've got an amplitude that you apply on the inside at the input side, and an amplitude that you get as a result when you observe at your state variable. So we call the magnitude ratio the ratio of those two. So the amplitude of the output, so if that's AY divided by let's call it AX, then that's your magnitude ratio. And you see here, there's nothing, we are not saying anything about Laplace transformations or anything like that here. At the moment, we are purely talking about in the time domain. So in time, if we apply a sine wave input, we get a sine wave output, and we take the ratio of the amplitudes, and then that's our magnitude ratio. And then also, if we have started, let's say our sine wave was doing this here. So the input sine wave looks like that. And then we can see the output is here. So this difference, the difference in time between the input and the output, we call that theta, right? And so we get the magnitude ratio, and we get the phase angle. So once more, the magnitude ratio, that's the ratio of the amplitudes that you get. And then the phase angle is, if you like, the time delay between the two. So let's say your input signal was like this, then you can see there's this difference, there's this offset between the two curves. So we call that the phase angle. So MR and theta, I hope you'll agree, is something that you can measure directly from the process. And in fact, you already did that in your practical. You applied a sine wave and you measured a sine wave and you worked out a magnitude ratio and a phase angle. So that's all fine. So we can measure these two functions. Now, what the basic theorem is telling us is that if we go and measure those, we will get the same if we had the transfer function of this process. So remember, for the whole process, we can identify a transfer function, and let's just say it's this GP for now. So if we apply I omega in that transfer function, then we will get the same measurement, right? So this one we measure. We don't know anything about this as yet because we've said, what if the process is a complete black box? So we don't know what this function is, but we can actually get the values of this function along I omega, right? Which seems like a very strange and specific thing. So we don't quite know yet what to do with this result, but this is one thing we can say. And so in the last contact session, we derived this relationship. You can, of course, look in the notes and look at that derivation, right? So now we want to answer, why does this matter and how can we use this fact for the purpose of control? Right, so towards doing that, I've broken it down into a number of steps. Well, the number is 4. I've broken it down into 4 steps. And so step 0, actually, so it's 5 steps if you include step 0. Step 0 is just, are you comfortable with working with the complex plane? So when we want to work with this complex plane, first off, we are trying to understand the function g of s, right? We know g is the transfer function for our process, and s is a complex number. So in the complex plane here, we can talk about s. So of course, the real part of the complex value s, the real part is shown as the x value, and then the imaginary part is the y value. Right now, we can pick a point on this complex plane, and then that defines a value for s. And now we have some function of s. For example, g might be s squared plus 1, right? And so if g is s squared plus 1, then we can talk about a corresponding g plane. So s is a complex number, g is another complex number, and we can observe what g is doing as we choose values for s. So once more, if we choose one value for s, then that defines one value for g, right, according to whatever relationship it is. Then if you go and choose another value for s, then that gives us a different value for g. And so we can choose any arbitrary path in s. We can choose any set of complex numbers for s. And then if we apply that in the function, then that's going to give us a different set of complex values in g, right? So to really understand what we'll be doing for the rest of the session, it's important to see that we understand this, this first step. Any questions or comments on this part? Right, so once more, s is a complex number. It has a real part and an imaginary part. So when we pick one point, that defines one value for s. And then if we apply that in our function for g, that defines a different value for g. And then we can choose a series of s values. And so that will define a series of g values. Right, so just be sure that this first step, you're quite comfortable with that. Then the next step, or in fact, these are not really steps. These are more like different facts that we have to bear in mind, and then we'll see how the whole of control works. So the next thing to recall is that if you have a function like this, let's say this is our transfer function. If our transfer function, right, normally it's written in G or something like that. If it's of this form, 1 over s plus k, then minus k is a value of s where this function goes to infinity, right? So we call the value s equals minus k a pole of this function, right? So a pole, we think of that as something that sticks up very far. So a pole is a value where the function goes to infinity. So y goes to infinity when s gets close to minus k, right? So minus k is a pole of the function y. And if you follow the developments in the that we showed in the lectures, it turns out that the poles of this function are the time constants in the time domain, right? So here we were talking about in the Laplace S domain, we know that we can translate it to the time domain. So in the time domain, we'll get an exponential term, and so it'll be e to the t, and then there'll be a constant in front of it. So minus k will show up here. So the minus k, which is the pole here, will show up here as a constant in the exponential. So we are concerned that if k has any positive real part, then this term is going to explode, right? For example, if this minus k turns out to be 2, then you've got e to the 2t. And so you've got the exponential of 2 times t. And you can imagine if t goes to, let's say, 1,000, then you've suddenly got e to the power 2,000. I don't think your calculator can even calculate a number so high. So we are very worried about ever getting a positive real part for this value of k. In other words, we never want the pole of our function. We never want that pole to have a positive real part, because it's going to cause our function to explode. Okay, any questions or comments on that? Okay, now, so that's another fact that we are going to keep in mind, right? So we are worried about the poles of our transfer function. So of course, you may need some time to review that, convince yourself that the pole of your transfer function shows up as the time constant. Now, the poles of interest to us, for the sake of control, the poles that matter to us are the roots of this function, right? And here I'm showing the development for that. So number one, we know that in our actual process, we are going to have some output y is equal to our transfer function times our controller, right? So we let u be the control function. So y is the output function. And now for the control function, we are typically going to base that on the difference between the set point and our current value. So in our process, we have a current value y, and we want to get to some set point y sp. So the difference between the set point and our current value is what we think of as the error. And so we want our control action to be proportional to that, right? So we want to take control action. So in the case of proportional control, we want the action that we take to be as large as the error that we are seeing. So in other words, if there's a big difference between our set point and our current value, we want to take big control action. If there's a small difference, then we don't want to take as much control action. So that's the idea in proportional control. So that's what we are looking for, or that's what we want to apply. And then if we translate this to the Laplace domain, then we've got big U equals, and there'll be some constant, or there's some transfer function GC times the Laplace transformation of these ones, YSP minus Y, right? So by the end of the day, this then becomes our transfer function. And so this U can be replaced up here. So now we can write Y looks like this. And now you've got Y's on both sides. You group out the Y's and it looks like this. And then you can rewrite this as Y is related to YSP like this. Okay, are there any questions or comments so far? Okay, now so now we have this transfer function. And now you can see here that the denominator is 1 plus GPGC. And we just said we are worried about getting a 0 in the denominator here. So the value of s where the denominator goes to 0, we call that a pole. And we know that shows up as a time constant and all that stuff. So we want to know, when does the denominator go to 0? And so we've just shown now, in the case of applying control, the denominator goes to 0 when this goes to 0, right? And by the way, we just lump together GPGC as G open loop. So we call G open loop GPGC. So we can see here, when 1 plus G open loop equals 0, then we've got a pole. And so we want to know, what are the values of S that make this true? So which S values give us 1 plus G open loop equals 0? Because those values of S will determine whether we are going to explode off to infinity. In other words, if we get any S values that satisfy this equation, and if those values have positive real parts, then this is not a stable process, right? And by the way, it's a short bit of logic here, but it's important to understand these steps well, right? Do you have any questions? Is that all clear enough? So when we're setting the assessment, this will be tested, right? The logic behind how we develop the controllers in frequency domain dynamics, that will be tested. So please do get this right. Do you have any questions on this? Right, so once more, just go ahead and follow the steps here and make sure you can see the pole of this, of y, is where this denominator goes to 0. And we are worried about the denominator going to 0 because the roots of the s values where it goes to 0 turn up as the time constants. So we never want to see a positive real part appearing in the s values behind this equation. Okay, so that's, if you like, principle number 2. So that's the second thing to remember. Now, in factoid number 3, if you like, we are using what's called the principle of the argument. So this comes from the field of complex analysis, where it's telling us if we have some function f, which has z zeros and p poles, right? So let's think about what that means. So if you've got some function, so here's the S-plane. So here's there's the imaginary part and there's the real part. And then you've got some function. So, and let's say this function has z zeros. So let's say at this value of your imaginary, in your imaginary plane, at this value, your function goes to 0. So if you were, so imagine that we were plotting what this function looks like. So let's say the function, so on this side, let's say it goes down to 0 at this point. So let's say this is the point x and that this is 0. So there's your 0. So at this value of x here, or at this point, you are getting a 0. So here I'm plotting this function f, right? So there may be a point in the S-plane where the function f goes down to 0. And then there may be other values where the function f goes off to infinity. So let's say there's another point here and another point here where the function is going off to 0. So it's going off to infinity here, and then let's say it comes back down, and then it goes off to infinity again here. So according to this, there are 2 values where the function f goes off to infinity, and there's 1 value where the function f is a 0. So you've got the 0 here, and then you've got the 2 poles, right? So that's the way we read this. We look in the S-plane and we say there's a 0 here, and there's a pole here, and there's another pole here. So according to the principle of the argument, if you have a function f that has z zeros and p poles, right, in some space in the z plane. So we are talking about a closed boundary here. So in some region, if you have z zeros and p poles, then as you travel around that domain, you will encircle the right-hand plane by an amount equal to z minus p, right? So first off, just understanding what that means can be something of a challenge here, but let's think about what we said at the outset. We said if we go and choose in the S-plane a certain path, right? So let's say this is the S-plane. So now we've chosen, let's say we pick this as a starting point, and then we travel around here. So we pick a series of values S, and so we use all these values S that are going around this boundary. And then we observe what is happening in G. So as we move around in S here, something is going to happen on this side in G. So G will respond and it will change in some way. Right, so once more, we are choosing values of S. So we pick a value of S, let's say here. So we've picked a value, then we stick that in our function G of S, and then we work out the value of G. So maybe that value of G is actually here. And then we move along this curve a little bit more. We get another value for S. We stick this new value of S in G. That gives us another value here. And so as we move around the S-plane, we are getting different values for G. Also complex, so that's why we're drawing it in a plane, right? Again, this is the imaginary part, and this is the real part. So we are plotting all the values of G as we vary these values of S. So S is going to be varied in this around this path, and we are observing what's happening with G as we do this. Now, the way I've drawn it here, we have encircled the origin. So this is the 0, 0 point, right? So what this theorem is telling us is if we have Z zeros, so let's say, well, these are two poles actually. So if you have, well, I just want to add two more zeros. Let's just say we had 3 zeros and 2 poles. Then it's telling us that the number of times we will go around 0 is equal to, so n is the number of times we go around the 0, right? So G started here, it's going around, so it's gone around the 0 and it's ended up here, right? So the number of times we go around the 0 is equal to the number of zeros that we have minus the number of poles. So we've said here we've got 3 zeros and 2 poles. So 3 minus 2 is equal to 1. And here we can see we've gone around the origin 1 time, right? And that seems pretty far out. How do we ever imagine such a thing is true? So the proof is shown here. And in fact, it's quite a simple thing. So if you have some function like this, so f equals s minus z1 times s minus z2 over s minus p1. So in this case, we've got 2 zeros and 1 pole. Then we can say that, of course, once we evaluate this, right, for some choice of s, so if we choose s to be some complex number, then you evaluate this, right? So your Zs and Ps, those are also complex numbers, right? Remember, we are looking in the complex plane here. So those are complex and S is also complex. So you can subtract them, multiply them, divide them, and then you'll get a complex number out. And so F is a complex number. And so we can talk about the argument of the complex number. Right, so of course, if you have a complex number, then there's the real part, there's the imaginary part, here's the 0. So the angle is, it has the imaginary part here, and the real part is here. And so the angle is the arctan of the imaginary part divided by the real part, right? So that's the angle. So the angle of this function f is equal to the angle of the right-hand side. And if you remember your complex analysis, and from some of what we did last week, the angle can also be obtained by taking the sum of the angles of the individual functions. So the angle of s minus z plus the angle of s minus z2 divide, and then you can subtract the denominator, so minus the angle of s minus p1. So if you think about this, as we go around the boundary, right? Let's pick a particular zero. Let's say we are interested in this zero. So this zero. And now we are taking a boundary that goes all the way around that zero. So let's think about what happens to the angle here. So let's take the zero here. And then let's say we are currently at this S position. Then you see your angle has gone through this value. And now as we travel around, let's say we get to this point, now the angle looks like this. And you can see as you travel around that point, you keep going into different angles.
Simulation. Cabanga ukuthi ngiqedile kodwa ngizocela umuntu ozoba khona ntambama ngenza interview.
I'm just trying to mute.
Ngibambisile kundla ngifuna.
Okay. Okay. So you see here, as we move around this S curve, the angle is increasing here, right? So going around the contour, we can see the angle is increasing for all the zeros. So the angle increases by 2 pi. That means in the G plane, the angle will increase by 2 pi like that. And then for all the poles, because that's in the denominator and there's a minus sign in front, it will go the other way, right? For each pole, it's going to do this. So for each zero, it will go forward and encircle 1 time like that. And for each pole, it will reverse and go around like that. So that's why as we go around all the poles and zeros in here, we change the number of times the function g encircles 0. Okay, any questions or comments on that? Okay, so this is why I say you need to spend a bit of time on this material, because it takes quite a bit of getting used to thinking in terms of the complex plane and so on. So what might be a bit hazy to you is you might need to revise your complex arguments and things like that. So go ahead and do that. And then you'll see this is actually quite a straightforward thing to realize. So we are picking a series of values of S, and then we observe what happens to G, and then the number of times that G encircles the origin will equal the difference between the number of zeros and the number of poles. So this is an important step, right? The principle of the argument, right? So again, we park that little fact, and we're going to come back to that just now. Now, the next thing is we want to let S travel around the entire right-hand plane and observe what happens with G. And if G ever encircles, I don't want to say -1, 0. Okay, let's keep it like this. So if G ever encircles -1, 0, then our system won't be stable. So this is the thing we need to understand, right? So number one, we want to encircle the entire right-hand plane. So I'm just going to make another one here. So we've got our complex plane here. Here's the imaginary part, and here's the real part. And we want to encircle the entire right-hand plane. And that sounds like a crazy thing to do. How do you ever encompass the entire right-hand plane? And in fact, the way I'm drawing this kind of suggests a way. So if you can imagine pushing this boundary out to infinity, then that gives us the entire half plane of positive real numbers, right? And obviously we are concerned about positive real roots, and that's why we're doing this. But I'm calling it a half plane because, of course, we are not looking on this side. We are not worried about negative real numbers. We are worried about positive real numbers. So we are going to push out this boundary all the way to infinity. And so that will let us consider all the values inside here. So we want to know, are there any poles inside on this right-hand plane? Right, that's the thing we are really worried about, because the moment we have a pole of 1 plus g open loop in this right-hand plane, then we are going to get an unstable system. And again, that all goes back to this, right? The pole is, the pole of this function relates to the time constant. So if our time constant is ever a positive real number, then that means it's going to be unstable because this term is going to become much too big. Right, so we are worried about this happening, that we have poles here. Now, how do we use that principle of the argument to figure this out? So this principle 4 is broken down into a couple of steps here. So first off, the zeros are the poles of the closed loop transfer function. So we already said this, right? So we've established that, yes, we are worried about the zeros of this function. We are worried about the poles of the closed loop transfer function, and the poles of the closed loop transfer function are where we have the zeros of this equation, 1 plus g open loop equals 0, right? So so that's fine. So this is the thing we are trying to figure out. Now we have this principle of the argument for some path, right? So the way that was written, it said for any boundary, you can write z minus p equals n if you choose any path in S. Now, in our case, if the path goes around the entire right-hand plane, then we can perhaps use this fact to figure out how many zeros we have there. The problem is that we have this minus p part in this equation also. However, if you think about it, if our process is going to be stable, right, then our open loop transfer function, our process, that also must not have any poles in the right-hand plane, right? We don't want our transfer function going off to infinity in the right-hand plane. So we don't want our transfer function to have any poles that have positive real parts. So as we travel around here, we are going to say, first of all, that p equals 0, that our process is not going to be, it's not going to have any poles. And for that fact, again, you need to look back at the notes and see where we discuss that. But we have no poles at the outset. So our process doesn't have any poles in the right-hand plane, the open loop transfer function. When we put in control, we don't have inherent instability, right? Now we are looking for a more subtle instability. So we know this p equals 0. So if p equals 0, then z equals n. In other words, if we pick an S, right, all this is in the S plane. So as we travel around S here and we observe what's happening in G, if G ever goes around the origin even one time, then that must mean that there is a pole in the right-hand plane, right? So because we've said here Z equals N, that's going to tell us that there is a 0 somewhere in here, right? Remember, we are worried now about this function, 1 plus G open loop equals 0. So we want to know, does this function ever have a 0 in the right-hand plane? And the way we do that is we travel around the right-hand plane here, and we observe what G is doing as we do that. So if we pick a point here, then that defines, maybe we work out the G's there. And then we move down to this next point that gives us a next new point, maybe that's here, and so on. So we travel around in S, and what happens is then we also travel around in G. And then if G happens to encircle the origin, then that must mean that there is a pole somewhere inside this boundary, right? According to the principle of the argument, it's going to mean that we will have a pole somewhere in here. And as we said many times now, the moment we have a pole inside here, we are going to have a positive real part, and that means the system is going to explode. So now we are interested in this function 1 plus G open loop. So the function that we are plotting here, this is actually the roots of 1 plus G open loop. Now we could say, well, instead of looking for the roots of this function, why don't we just look at G open loop equals -1. So instead of plotting, so this is the function 1, or the roots of the function 1 plus G open loop. Now, instead of dealing with that, let's instead plot for ourselves G open loop itself. And that might look like something completely different because it's the roots of this function. So now we are looking at G open loop. And in this case, we are concerned about roots of this equation. In other words, in this case, we want to know, when does G open loop encircle -1? Right, so that -1 just comes from here, right? We just take the 1 across. And so we are asking, as we move around this S plane, move around the entire right-hand plane, do we ever encircle the point -1 with the function G open loop? Or equivalently, do we ever encircle 0, 0 with the function 1 plus G open loop, right? It's the same thing. The origin for 1 plus G open loop, or the -1, 0 point for G open loop itself, right? And that's the criterion then. We go around the entire right-hand plane in S, right? So in the S plane, we go around the entire right-hand plane. We move around this trajectory here, and then we observe how G is changing. And if G ever goes around -1, then it means it's an unstable process. Right, so that's the next bit. Now the question is, so we've talked about this -1, 0 instead of 0, 0. So the question is then, how do we go around the entire right-hand plane? Because the right-hand plane is infinite, right? Even though it's half of all of S, it's still an infinite plane. So the way that we go around the entire right-hand plane is we pick 3 paths, and the 3 paths are shown here. Path 1 involves going from the origin straight up to infinity. So this is your S-plane, imaginary part and real part. So you start from the origin and you go up to infinity. And so I'm writing it like this. So the equation of the S values, it looks like this. There's 0 for the real part. So we are moving purely along the imaginary axis. So the real part is 0. And so we represent this as IR. So R is the distance we've traveled up here. So R is going from 0 to infinity as we go up here, right? Then the next part is, we reach infinity, which is a silly thing to say. We never reach infinity, but anyway, we're out at infinity. And then we take the semicircle that goes around the whole plane. So we're at infinity and we go around. We imagine an infinite circle that starts up here and it goes around until it reaches the negative imaginary axis. So we go around like this. So we represent that in this way. We say here the magnitude is this value r, which is going to infinity. So we are representing the complex number as in polar coordinates. So we represent it as a magnitude and an angle. So r is going off to infinity. So that's the magnitude. And we can see here the angle. So the angle here, remember, it's always the angle is referenced to the positive real axis. So that's our 0. And then the angle here, it starts at 90 degrees, right? So our angle here is 90 degrees. And then as we go around, then it comes down to 0, and then it goes negative, and then it goes minus 90 degrees. So we are going from 90 degrees to minus 90 degrees, or pi by 2 to minus pi by 2, right? So that's this part of the path. And then once we reach an infinite distance down the negative imaginary axis, then we crawl back in here. So we go from minus infinity into 0. So we are going up the negative imaginary axis, and then we are going from infinity into 0. So do you agree then that this path will encircle the entire right-hand plane? Right, so I'll take that as a crashing confirmation that you agree that this is going around the whole right-hand plane. Okay. Now we can think about simplifying this, right? You see, if we think about path 2, the magnitude of S is infinity, right? It's a crazy high number. And we know that our transfer functions for our process, those are all going to be functions that have this form. So it's going to be G equals I'm just going to write it as, we can write this as S to the power M plus A times S to the power M minus 1 plus da 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 until some other constant times S to the power 0, which is 1. And then in the denominator, we will have a similar thing. But this time, the order will be n. So, and the constants will be different here. So it's a different set of constants. So generally speaking, our processes have this form, or we can, using Taylor series expansions, pose them in this form. And in any controllable process, n is going to be greater than m, right? So your order in your denominator is always higher than the order in the numerator. And again, in the notes, we cover in some, well, not real detail, but we explain why that is. So you can go and read that part. But the order of the denominator, maybe let's say it conditionally here. If the order of the denominator is greater than the order of the numerator, then when S goes to infinity, the denominator becomes much greater than the numerator, right? So for example, if this is S cubed, whereas up here you only have S squared, if you apply a value of 1,000 for S, right, then 1,000 cubed is definitely greater than 1,000 squared, right? It's a factor of 1,000 different. So your denominator is going to be much greater as you increase the value of S. I only used 1,000 there, right? But as S goes to infinity, this denominator is going to become much, much greater than the numerator. So this value for G is going to be a 0. So all along this path, the value of G is approximately 0. In other words, the function is not going to go close to the -1,0 point, right? The function G is going to be close to 0 in that region. So it's pointless looking for poles by going through this part of the path, right? So in a sense, we can say, yes, I know I'm looking for poles, but I know I'm not going to find it by going through this middle path. The other side of it is we have a kind of symmetry here. So you are going S equals I omega plus I omega here, and you're going S equals minus I omega here. So these two paths are complementary. So you are going to get the same information on paths 1 and 3. That means you might as well just look at path 1. Only path 1 is going to give you new information about G. Because remember, the information we want is how much is G going close to -1, 0. And we can see every possibility for going close to -1, 0 just by looking at this part, right? When it's going around here, G is always close to 0. So that's not going to give us instability. And if we go up this way, then G is just going to go over the same values again. So it's pointless looking at those two other paths. We might as well just look at this path, right? And we've said here S equals 0 plus IR, where R goes not to infinity. We can just change, instead of using R, we can call it omega. And now you see S equals I omega. And that brings us all the way back to our first statement here, that G of I omega is equal to the magnitude ratio, and the argument of G of I omega is the phase angle. And we know that we can get these two functions. So we said from applying a frequency experiment, if we apply sine waves at the input and measure the output and take the magnitude ratio and we take the phase angle, so we know we can get this even from the time domain. We can construct this function. And it turns out that exactly the function we need, right? We need to know how G is varying in the S-plane. So it turns out we can actually go and measure this. And that's a great step forward for us, because up to now it has been this headache. Well, I need to derive the equation for my process, and then I need to translate it into the Laplace domain and do all these things, and eventually I'll get a G, and now I still have to go and apply I omega, and then if I watch what I omega does, then it can tell me something. Well, now it's saying you don't need to do any of that. Now we are saying all you do is apply different frequencies here, and you'll get different magnitude ratios, and you get different angles, and then you just go ahead and you plot that. And so if you plot, if the magnitude ratio is the same as G of I omega, it's it's the absolute, it's the magnitude of G of I omega. Right, so that's giving us the magnitude and how that's varying. And then the angle here is the same as the angle for G of I omega. Then that means we can draw G of I omega directly. We can go ahead and just draw this G function. And we can look at, am I encircling -1, 0? So you see, now we can deal with any system. It doesn't have to be a system we can model. It doesn't even have to be a system that we know anything about. Our process can now be a complete black box. We don't know anything about this process. The only thing we do with this black box is we apply a sine wave to the input, and we measure the sine waves coming out. And then that gives us a magnitude ratio and an angle that gives us 1 point here. Then we go and we change the input frequency. So we use, maybe we use a higher frequency now. Then that gives us a different magnitude ratio and a different angle that gives us a new point here. And so we keep changing the frequency and constructing these different points here. And the only thing we need to do then is observe how close the locus of points comes to -1, 0. And if it encircles that point, then yeah, if unfortunately it does this, then we know, no, this is unstable, and my controller is not good. So so I haven't shown the controller here, but you know, obviously there's some control action we are taking here. So so there's some controller setting here, so K. So we can say, oh, the controller is too extreme. Please drop your values of K. So we reduce the values of K until we are not encircling -1, 0 anymore. And then we can say, okay, now the system is nice and stable, and you can control it like that. Right, so that's the logic that we need. We just need to know what do we do to get G? How do we get G? And in fact, it's a specific path of G, right? The path of G that we get when we apply I omega. And it turns out we can very easily get G of I omega using the sine waves at the input. And then the other thing is we need to know what to do with it. So all this complicated stuff about complex analysis, it reduces to this nice simple fact that as we observe what happens to G, if G ever encircles this particular point, then it must mean that there is a pole of the function 1 plus G open loop in the right-hand plane, and that means it's going to be unstable. Okay, any questions or comments there? And so please follow this line of logic very carefully. Be able to answer anything about this, because this, in essence, is exactly what this half of the course is all about. There's nothing more complicated than this, right? And in fact, none of this is complicated either. It's just that it feels a bit unfamiliar because we are not so used to dealing with the complex plane. But the moment you get a bit comfortable, even with just understanding the angle of a complex number and so on, then the whole thing just follows automatically. So this is not complex logic to follow. Just make sure you work through it carefully and are able to answer questions on any aspect of this. All right, so that's the first part, right? So that's just the logic. That's just telling us now how we can construct the function G and why the point -1, 0 matters. Right now, once we understand that much, then the rest of it is a simple matter of determining what the control parameters should be. And what we have available to us is the Bode diagram. And I did this in some detail in the last contact session. But in our Bode diagram, we are defining the so-called log modulus. So it's defined as 20 log 10, the G open loop function. And in fact, it's not actually correct. It's G open loop at I omega. Right, so you take your transfer function, you apply I omega, and then you take the magnitude of that. So that magnitude, the log 10 of that times 20, that's your log modulus. And the reason we do this is because it has some really nice properties for us. And I just want to say here, this is G. So that's here. So if we think about this, you can see here, if we are applying a proportional controller, we know that's going to introduce a Kc times the process transfer function Gp. And so that's our G open loop transfer function, right? So if we stick a G open loop equals this in here, then of course that's going to be Kc Gp. Now Kc, in the case of a proportional controller, Kc is not a function of S, it's just a constant. So we can split this, right? The log of the product of two functions is the sum of the logs. So it's 20 log 10 Kc plus 20 log 10 Gp, right? That's the product rule for logs. And now if we look at this function, we can see here something that's log GP I omega, and you've got here 20 log 10 KC. So that means the proportional part is going to add an offset here. So in other words, if you have, let's just clean that. So if you have a plot of L versus log omega, and let's say we didn't apply control, let's say this was just GP. So let's say it looked like this, right? So this is our plot of GP. In other words, we've gone and we've worked out, we've gone and worked out the, this should say magnitude, by the way, the magnitude of GP of I omega. So we've got this part, so we plot 20 log 10, the magnitude of G I omega, and then we get a curve like this. Then as we introduce a proportional controller, all that's going to do is give us an offset by this value. So for example, if Kc is a value of 10, right, then log 10 of 10 is a 1. So then this is going to be a 20. Right, 20 times a 1, right? So 20. So that means this whole curve can just shift up by 20. And so we get the same curve as before, just that it's shifted up by that fixed amount, right? So a P controller is then just going to shift our L vertically. So in a Bode diagram, it's going to just shift our plot of GP vertically, and the amount of vertical shift will depend on the value of K that we apply. Right, so for the Bode diagram, that's what happens. Now that's only half the diagrams. The other half of the Bode diagram is it's also the angle. So you're also plotting theta, which is the argument of G I omega. And this angle is, well, yeah, that angle is of the function G of I omega. So you look at your function and you determine the angle of the complex number that you get. Now, in this case, if we are considering the proportional part, this is only a real number. And the real number contributes a 0 angle. So let's just plot a real number here, a pure real number. Right, so if you have a pure real number, that means you're moving on the real axis. In other words, your imaginary part is 0. You can see here that the angle between this and the real axis is 0. So for a proportional controller, your angle is not shifted at all, right? Your proportional controller won't change the angle. The only angle you have to contend with is the process. So we should specify here that only comes from the process, not from the controller. Okay, so for a proportional controller, we are just shifting horizontally on L. If you look at the angle part of it, if you are plotting theta as a function of log omega, if you plot your G function, whatever it is, as you change your value of Kp or Kc, whatever you want to call it, it's not going to change that. You can use whatever proportional value you want. Your angle part is not going to change. So your Bode diagram will have this influence. You start out with a particular process, and then as you apply different values for Kp, that's going to shift your curve vertically for the L, but for theta, it's not going to move that at all. Okay. Just give me a second. I'm just going on mute for a minute. Okay, sorry about that. So, so that's how we draw our Bode diagrams. Now, that's what we can do for the proportional controller. If we have a proportional integral controller, then we can show that this expression applies. So remember, for the proportional integral controller, you have the proportional part. So here you can see Kp times the error. That's so the control action is proportional to the error itself. And then the integral part is where you integrate the error over time. And we use another constant over there, another tuning parameter there, tau I. So in this case, the integral of the error is proportional to, or adds a part that's proportional to the control action to be taken. And if you recall the Laplace transformation of the integral, that gives you 1 over Ks times the transformation of the kernel. So you get a function like this. And then if you if you group out these two, so you can group out an ES here, and then of course we want the transfer function, so U over E, then that leaves us with 1 plus 1 over tau S. So that's what you have. And then you can rewrite that. You can put both terms in over tau S here. Right, so that's the transfer function for your PI controller. And if you followed the notes, if you are up to date with the course, you will know how to read that. Let's just look here. So for the Bode diagrams, this is what we have. So so this is what we just talked about, right? We said if G is just Kp, then it's just a vertical shift and the angle doesn't change. If we have a first order lag, then the magnitude ratio is where G is I omega. So it's K over 1 plus tau I omega. And then we don't like any imaginary number in the denominator, so multiply numerator and denominator by the complex conjugate. And then it looks like this. And so your magnitude ratio looks like that, right? So you can see here, anyway, we'll come back to this with the log modulus. Okay, we don't actually, so let's just do it here. So from this, we can say L equals 20 log 10 of this stuff. And that's equal to and now we can split off a constant, or let's just rewrite this like this. We can rewrite this as K times. Oops. So we can rewrite this as K times 1 plus tau squared omega squared. And this is all raised to the power minus 1 over 2. Oops. Minus 1 over 2, like that. Right, you agree? 1 over the square root of 1 plus tau squared omega squared is the same as 1 plus tau squared omega squared raised to the power minus 1 over 2. And then we can rewrite this using our product rule as, we can split off the K part. So that part we'll write here as 20 log 10 K, and then plus that. And now you've got this minus 1 over 2 here. And again, using the property of logs, you can take that as the factor in front of the log. So you can get rid of that and instead make this minus 10. Right, so we get rid of that part, and now we have a function which we need to plot, and we need to think about an efficient way to plot this. So a clever way to do it is to consider the values here that matter. So first we can say, so if omega is much less than 1 over tau, right? Let's think about that. If omega here is much less than 1 over tau, then this thing is going to be much less than 1. In other words, this becomes a log of 1, which is a 0. Then, so we can say here, the second term is approximately 0, right? Right, so once more, if omega is much less than 1 over tau, then this product is going to be much less than, well, this is going to be much less than 1. So overall, this is a 1. So it's log 10 of 1, which is a 0. So that second term becomes 0 for low values of omega. On the other hand, if omega is much more than 1 over tau, then you can see that this whole term is going to be much more than 1. And then this second term is approximately minus 10 log 10 of tau squared omega squared, which we can also write as minus 20 log 10 of tau omega. Right, so when omega is much more than 1 over tau, then it becomes minus 20 log 10 tau omega. And in fact, one more thing we can do here is split this up. So we can say this is equal to minus 20 log tau and minus 20 log omega. Right, so that's going to tell us that the way to draw this is then using this. We can simply say that when it's much less than 1 over tau, then we have just a fat 0. And then when we are much more than tau, then the slope equals minus 20, right? Because we are plotting against log 10 omega. So we are plotting here log 10 omega. So if log 10 omega is actually your x, then the factor in front is minus 20. So that tells us it's just going to decrease on a straight line like that. So even though this function looks complicated, by the end of the day, we can plot it very, very easily. That's the beauty of Bode diagrams, and that's why we use them so much in controls. We just find this point where we transition from one asymptote to another, and we've noticed that to the left it's a 0, and to the right it has a drop-off of minus 20 there. And so that's how we plot that diagram. Okay, so that's the Bode plot for the so-called lag. And then you would read all this, and it would talk about the lead and how to draw so you can follow these developments, and you can get a similar thing. And this time you'll show the slope is plus 20, and they call it decibels per decade. So per decade, because this is on a log scale, so it's factors of 10, so decibels per decade. Right, so that's how you draw your Bode diagrams. So in terms of a PI controller, we can acknowledge that we can draw a first order lead. So we just saw a first order lead here. So we would draw this part, and then we would draw a 1 over tau I part. And so what's convenient is that on Bode diagrams, you can just add together the different lines. So if you have a function that looks like this, let's just take an example. If you have a function g equals f1 and f2, then when you calculate the log modulus of that, it's going to look like L equals 20 log 10 f1 plus 20 log 10 of f2. So that means you can plot each pair of lines separately. So on your Bode diagram, you plotted one set of lines, for example, and then maybe you plot a different set of lines here. So maybe you plot a line like this. So maybe you find the other function actually looks like this. Then it's a simple matter of just adding these two together. So you can see here, when you add these two lines together, this if this is 0, then the sum of those will be this value. But at this point, then this function starts to go up. So we'll follow this, and it will keep going up. Then you reach a point where this graph is no longer 0, it's starting to go down, but maybe it's going down at the same slope that this one is going up. So then the sum of these two will actually be like that. So that's the beauty of the Bode diagrams. You can plot the individual functions, and then you can just graphically add them together. So that's what we do. And I've set up this example here. So let's work through this example here. So we want to consider now that we've got some process like this. So our actual process, once we do the transfer function and all that stuff, it works out to 1 over 5s plus 1. So we want to know what are the parameters of a PI controller that will control this process. So to figure it out, first we apply I omega for the process. So S becomes I omega over there, which we don't like in the denominator. So we multiply by the complex conjugate, and then we get the form that looks like this. And then we want to rewrite this in polar coordinates. So at the moment it's written in Cartesian coordinates. Notice here that we've gotten rid of the imaginary part in the denominator. So this is in Cartesian coordinates. So we convert it to polar coordinates by working out the magnitude of this complex number. So we take the real part squared plus the imaginary part squared and then square root of that. And if you work through it, you'll see it works out to that. And then the angle of this is the arctan of the imaginary part divided by the real part. So of course, if you're dividing, then the denominator will cancel out. So it's just this imaginary part divided by that real part. So minus 5 omega divided by 1. So it's arctan of minus 5 omega. Right, so this is what G looks like in polar coordinates. And then we want to first graph the L part of this. So we want 20 log 10 of the magnitude of G of I omega. So there's the magnitude of G of I omega. That's why doing it in polar coordinates is nice. You can straight away see the magnitude. So that's our magnitude. And then you can rewrite this as 1 plus 25 omega squared raised to the power minus 1 over 2. You take the minus 1 over 2 in front as a factor, and that becomes minus 10 log 10 1 plus 25 omega squared. Right, and then you look at this this equation, and you can say, well, I can think about the two asymptotes here. So if my omega is much less than 1 over 5, then this number will be close to 0. And so this becomes log of 1. So for very low values of omega, L equals 0, right? Log of 1 is a 0, so L is a 0 there. And then also, if you think about your angle, right? Your angle here, it's the arctan of minus 5 omega. So if omega is very small, if it's close to 0, then it's arctan of 0, which is 0. So your angle is also 0 there. On the other hand, if omega is much more than 1 over 5, then this number will be much bigger than 1. And so this whole thing becomes approximately 25 omega squared. So it's minus 10 log 10. Where's the 25? This should say 25 omega squared, right? And then we can, well, what we should have done is written this as 5 squared omega squared. So then you can rewrite this as, you can take that, the power of 2 as a factor in front. So it becomes minus 20 log 10 5 omega, right? And then that you can also separate out. So you can rewrite this as minus 20 log 10 minus 20 log 10 of the 5, right? Because we want to figure out how to plot against that log omega. So that's what happens to L for omega much more than 1 over 5. Then in terms of what happens to theta, again, if you look at the angle, if omega is much more than 1 over 5, this is then much more than minus 1. So this whole thing becomes the arctan of minus infinity. And the arctan of minus infinity is minus 90 degrees. So let's see if we can use these two facts together to draw our solution, which is what I've done here. So here's L plotted against log 10 omega. So for low values of omega, L is 0. And then as we go past 1 over 5, it has a slope of 20. Right, so for large values of omega, you end up with a term here minus 20 log 10 omega. So you get that that slope there. So that's the L part. And then in terms of theta, we said for low values of omega, theta is about 0. And then for high values of omega, theta equals minus pi over 2. So that's what that looks like. It starts at 0, and then it becomes minus 90 degrees. Normally, we draw this with a bit of a curved line and a curve there just to show the transition region, because remember, these are just asymptotes. So there, that's a quick way to draw a Bode diagram for the process itself. So far, that's only about the process, right? We haven't yet talked about the controller, because that was the question, right? Here's the question. Let's just put this on a new page. So that's the process itself. So that's the process itself. Now we want to implement control on this. So for the controller, we just showed just now that the controller, right? So just notice here, GC, the transfer function for the controller, we showed that that's equal to this thing, right? So if you just look up at what we talked about over here, right? We had just talked about when we use a PI controller, we said this is what you get, right? So we're using the same thing now. So I'm just repeating it because that's not part of the question. In the question, it just says it's a PI controller. So if it says PI controller, then it means we've got this. Now, we want to plot the Bode diagram, so we have to use I omega. So we stick in for S, I omega. Sorry about that. So S equals I omega, so you make that substitution in there. And then here, what did I do? Oh, here, I'm just splitting off that KP part. So let's use the product rule here. So KP in its separate term to this part. And then we also split this part. So you can regard this as the product of the function tau I omega plus 1 and the function 1 over tau I omega. So we just split those into two separate functions like that. And then the magnitude of this is, of course, the square root of the sum of the squares. And then the square root, we can take a half, right? It's to the power a half, so that becomes 10 over there. And then here, this is, if you like, tau I omega raised to the power minus 1. So we can bring the minus out here, and it looks like that. And then we can think about how to draw this part now. So first of all, the proportional part we know is just going to cause a vertical shift. There's no imaginary part to this. So let's plot the contributions from each of these terms. So let's plot this first part here. And I've already done that here. So here's the first term, the proportional part, right? P here is for the process, not proportional. So the process, we talked about this part, right? So the blue line, that's the process. We already drew that just now. Although I must say, I can see a bit of an error here. It's 0, so it's 0 there, and then it's, yeah, so there's just, yeah, this part here shouldn't be there. So anyway, that's the process, the blue line, and then the red line is now the proportional part. So the proportional part is 20 log 10 kp. So there's 0, there's 20 log 10 kp, so that's the red line. And then in terms of the angle, we said the angle for a proportional part is 0. So there's the 0 going through there, right? So that's the first term. The second term is this thing. And then in this case, if omega is much less than 1 over tau I, then this thing is much less than 1. And so this whole thing becomes a 0. So it's 0 for omega much less than 1 over tau I. And then when omega is much more than 1 over tau I, then this is much bigger than the 1. So you can ignore the 1. And then it simplifies to this. And then you can take the power 2 out in front and split them apart, and you get that. So for the second term, it's a 1 up to 1 over tau I. So for term 2, we show 1 over tau I here. And just be careful, the 1 over 5 we had earlier from the process, that's generally different to the 1 over tau I. So you show separately a 1 over tau I. So it's 0 up to 1 over tau I, and then it increases with that offset of log tau I. So it increases with 20 log 10 omega after 1 over tau I. So that's the L part. And then for the theta part, it's 0 for low omega, and then it goes to plus plus 90 degrees as omega increases. So the angle part 0 and then plus 90 degrees. So this is the contribution from the second term. And then for the third term, yeah, the last term looks like this. And in fact, yeah, it's a little different. Yeah, no, it's the same thing here. So here, clearly, the magnitude of this is simply tau I omega. So in this case, and this should be a capital I. Right, so in this part, remember omega is the variable, is our x. So when we plot this, we are plotting log omega. So we have to separate that omega here. And so we just split these two apart, tau I and an omega part. And here you can see the gradient is minus 20 and then you have this offset, which is like a constant. So for this third term, we are going to get, it's going to simply be a minus 20 all the way through for L. And then for the angle, it's going to be minus pi by 2. So there's a constant minus pi by 2 over there. Okay. And actually, if I look at this, this is drawn correctly. Well, it's supposed to be across tau I. I think that's that line. Okay, anyway, um, just check. I think there might be a small error here in this number 2, but let's just accept for now that this is how it's supposed to look. So if this is correct, we've now drawn all the asymptotes for each of the terms involved in this process and its controller. Now the next step is we want to know what the whole controlled process looks like. So we have to add all these together. So the way you do that is you look from left to right and you look to see where the gradient is changing or where the asymptote changes are. We know the asymptote changes are at 1 over 5 and 1 over tau I. Now, if you look here, you can see that it's 0 here. So this these lines are not going to add anything. But here you are adding 20 log 10 kp. So that's an offset that you have to add. And then that down here, you get a, you are subtracting at a slope. So this is going to cause your total to go down. This is going to add a constant offset. So you can think of going up here, then you have to subtract off this piece. So maybe it gets you only to here. And then you need to go down at that angle. And then you're going to reach this point. At this point, you also have this line kicking in. So this is going to cause you to go even more negative. So it's going to cause you to go more negative faster. So your slope will double. If you were dropping at minus 20, then you've got another minus 20 from here. So then that becomes a minus 40 slope. So here's, it's shown here. So I didn't show that offset too well here because these two values, right, 0 to red and 0 to green are not necessarily the same, right? But anyway, so we start here, then it's first dropping at minus 20, then the blue line kicks in and it contributes another minus 20, so the slope doubles. But then you get to this point where you get a positive 20. So minus 40 plus 20 becomes a minus 20. So now the slope goes back to minus 20 here. So this orange line is the total amount now. And then you do a similar thing for the angle. You add together all the lines. You've got zeros here. You've got minus 90 here. So you've got minus 90. And then when you get to 1 over 5, the process gives you an additional minus 90. So now it goes to minus 180. So that's down there. Right, so that's how you get the overall the overall process behavior on your Bode diagram. You use the asymptotes, you sketch out the graphs quickly and easily, and then you just graphically add them. So it's very nice and easy to use a Bode diagram. And now what I'm showing is that what I want to do is use the Bode points to draw my curve. Right, remember, I want to know about whether it encircles minus 1, 0, and all those things. So to do that, what I'm actually doing here is choosing different values of log 10 omega. So remember, my x-axis is log 10 omega. So I'm choosing a series of values here, and then I'm pulling out the L and theta values. And I'm pulling them out because now I want to plot them on a Nichols chart, on a so-called Nichols chart. So a Nichols chart, you can see lots of lines on this Nichols chart, but don't worry about these curved lines for now. Let's just look at this L and theta, right? So your y-axis is L, and it says here open loop, L open loop, and the x-axis is your theta open loop also. So in contrast to the Bode diagram, which draws L against log of omega and theta against log of omega, we are now plotting L against theta, right? So you can see here, if you pick a specific omega value, then that's going to give you an L value and a theta value. So all you do on a Nichols chart is find L and theta, and that defines a point. So for example, this point, maybe that point is this point. And then you go to the next one. What's L at this next value of omega? So you choose another omega. There's my L value and there's my theta value for that omega. Then that defines the next point and so on. So you just span across your Bode diagram to pull out your points here. And then that gives you this curve on this Nichols chart. Now, that's all well and good. What about these curvy lines? They look quite exciting, right? So those curvy lines are from the closed loop transfer function. So remember, we are doing all this open loop, closed loop. We are looking at the open loop function, but actually when you implement control, the process is closed loop. So if you go back and check what we did last time, your closed loop transfer function is like this. So to plot what the closed loop transfer function is going to do, we simply acknowledge that the open loop transfer function, so if you like, this was GP times U. By the end of the day, this is some complex number, right? We know there's a lot behind it and there's lots of thinking and so on, but once you stick the functions in and once you choose a complex number, you are going to get a complex number as a result. So it's some complex number by the end of the day. And we can then represent it as a magnitude and an angle. So that's our standard polar coordinates of a complex number. So we can stick that complex number in these positions for the corresponding closed loop function. So it's going to look like this. And so we can say that the closed loop, so even this, by the end of the day, it's a complex number here over 1 plus a complex number. So we can work out what this is. We can rewrite this as another complex number. So we can say there's the equivalent closed loop complex number, which will also have a magnitude and an angle. And now we have a relationship between the closed loop complex number and the open loop complex number. And so it looks like this. And we can use this relationship to determine the magnitude of the closed loop transfer function in terms of the open loop transfer function. So if you do your transformation, right, the details are shown in the notes. If you do your transformation, you'll find this is the relationship for the magnitude of a closed loop function, and this is the angle for the closed loop transfer function as well. So with this, we can then say, well, now we have a nice relationship between the open loop and the closed loop. So on the right-hand side, these are all open loop values, right? The magnitude of open loop, there's the angle of the open loop. So there's nothing about closed loop on the right-hand side. It's all about the open loop on the right-hand side. So that means on a chart like this, if we are plotting on X and Y, the open loop values, then we can just work out for let's say R, let's do all the magnitudes first. So we just stick in the values of R and theta. So let's say at this point, let's say at this point, we stick in, there's an open loop, maybe that's a 16 over here, or maybe a 15. So plus 15 for L, and then minus 100 for theta. So you stick R equals 16 and theta is minus 100 in here, then that gives you a value for R. And then the curve that's drawn here, well, it's actually the dashed line. The dashed lines here are all the closed loop magnitudes. So when you stick the open loop values in, you'll get a closed loop value. And if you keep doing that, you will create a contour here. So you can figure out for all the closed loop magnitudes of 0.5, this is the locus of points on the open loop plane that gives us that. And then you can do the same thing for the angle as well. So that's a very convenient plot to have. So we can use the Nichols chart now to obtain all the closed loop values when given the open loop values. So we just go and use the Cartesian coordinates. We just use the rectangular coordinates to plot our open loop values. And then we look up. So let's say we were at this point, then we can see we are close to -60 for the angle. And in terms of the dashed lines, we're close to -6. So we can say this point is close to -60, -6 in terms of the closed loop, right? And if you look back in the notes at performance, so I think it wasn't the last one, but the one before, when we talked about the performance of these controllers, we said that when we have the 45-degree line, we will get good performance. So at the 45-degree line, we get good performance. So that corresponds to a closed loop L of 2. So if we can get our function to be close to this line, then we know we have a good controller, right? So this specific value, it's often used in control. LC equals 2, a closed loop log modulus of +2. That is a desirable control state to have. Now, going back to our example, we've got these values of L and theta, and we've managed to draw all these points in here. So this blue line is where we currently are. If we want to be tangent to the +2 line, we can then, and let's say we were only changing the proportional control. So only changing proportional control will shift this line vertically. So if we increase our proportional control, this blue line will shift up, and then we can stop when it becomes tangent to the +2 line over here. So we become tangent to the +2 line, and then we can say, I can work out what the proportional value must be if I want that to happen. So if we look here, we can see we are tangent to +2, maybe around here. And so it goes from, that's, let's say, a -4. And then down here, that's maybe a -16. So -4 minus -16, that's a -12. So that's a shift of a +12. So our blue line has shifted up by 12. So we can say our delta L is 12. And we know from our controller that delta L equals 20 log 10 delta Kp. So we can invert this equation. You can divide through by the 20, and then it's log 10. So you can take 10 to the power. So 10 to the power delta L over 20 is equal to delta Kp. So we can say here delta L is 12. So 12 divided by 20, and then 10 raised to that power is equal to the proportional controller shift that we want. Okay, so that's how you implement control. This example takes you through it. It takes you through all the necessary steps. So it shows you've started out with your process. You've figured out how to represent that in polar coordinates. You then translate that into the Bode style log modulus. You work out the log modulus and the angle for the process and for the controller of interest. Then that will give you then you add them together graphically. And then you take sections and you assemble your points. Then you use those points on your Nichols chart, and then you figure out what you need to do to get close to the +2 closed loop log modulus line. And then you know you've got a good controller. Okay, so that's kind of the recipe, right? But obviously, I don't want you to know just the recipe, because the recipe will only work if the conditions are exactly the same for that same recipe. Here's all the logic. So in the first hour, we covered all the logic as to why this works, right? First, we want to understand why that point -1,0 is important, and it's because of the zeros of this function being the poles of that function, and then it turns out that that is the same as the time constant there, which we don't want to be positive, and then we use this principle of the argument. So we know that in our function of interest, we want to watch how many times that function encircles the origin, and we can prove why that works, why that's true. And then based on all that, we can figure out that is the right criterion for us to use. And then the stuff about Bode and Nichols, that's just about how do you go about plotting all of that? How do you go about constructing a graph so that you can assess whether or not you are close to that -1,0 point? So be sure that you follow all the logic of these steps, and then that you are able to apply that using Bode diagrams and Nichols charts to tune your controllers. Okay, any questions or comments on that? So if you like this document, I'll put this on Dropbox just now. This one covers all the logic in frequency domain dynamics. This is basically what it's all about. If you can follow all these steps, this is basically the section done, right? And you see, it's really quite clever, right? The complex analysts, they've really given us a fantastically simple way of developing a controller. So this is about the stability side of it, of course. There are other things to control, but it's really quite amazing, right? The fact that you can, without even knowing the transfer function, right? This GP, right? All of this, the way we did this example was for a given transfer function, but you don't have to have this. You don't need to have this transfer function. Excuse me. So even if you don't know the transfer function, you can still construct this diagram. So yes, in the way we did this example, part of this was just for the sake of experience in how to work with these functions. But you didn't need this. Actually, you could have gone straight to this line. Remember, as we said, if you do frequency, if you vary your frequency and you collect your magnitude ratio and your phase angle, then you can go straight ahead and construct this, right? For L, you just apply 20 log 10 of the magnitude of G, which is the magnitude ratio, and then there's the phase angle. So you can just jump directly to this. So it's incredibly simple, right? All you need to do is apply a sine wave at the input, or a series of sine waves with different frequencies. Then that will give you different magnitudes and angles, which you can plot here. Then you just choose specific values. You then go and plot it on your Nichols chart. And then you can look at how to shift around on the Nichols chart. So we know KP goes up vertically. If you follow what I've written in this document, you'll also see that you can shift horizontally for if it's PI controller. So the I part also allows for horizontal shifts. So you can move your process around this plane. You can tune your controllers and really get some great performance there. Okay, so that's it. Any questions or comments? So if not, then that's it for today. And I guess we'll contact about whether we are doing a revision session and all those kinds of things. So that's it. Thank you. See you in the next one. Bye.